Hello and welcome to another sorting algorithm video. Today we're going to look at insertion sort. You'll find that it's got similar runtime to bubble sort, but in its average and best case, it actually works out better than bubble sorts. So let's jump on in and start sort of thinking about the algorithm and what we're going to do. So let's have a look. We've got bubble sort there. We've got insertion sort class around the place. Right, so literally we can go off and touch insertion sort.java. Now we've created the blank file. Now we can do a VS Code, perhaps, and take a look. We've got bubble sort there, we've got the class and stuff. Insertion sort, we're going to create. So last time, I made the functionality, then I put it into a class. For now, I'm gonna write the class to start with. So I've got this class wrapper. So public class insertion sort. Inside here, we're going to make a public static function or method, which will sort some data. So I want to kind of stipulate what it is that I'm going to do. So I'm going to make like a doc string. Let's say that this sort an array of integers, let's say, in ascending order, using the insertion sort algorithm. It's going to take in some parameter, and the parameter will be the array. So I'll just say ARR. Let's say it's the integer alphabet type. Off by 1 on the keyboard. The integer array to be sorted. Okay, now got our parameters, we've got a doc string, we've got that set up. So let's make a public static void. It's going to be an in-place algorithm again. Insertion sort. It's going to take an integer array, or they are. So the concept of what we want to do, we want to kind of, first thing, just for completeness of similarity of bubble sort, I'm going to say int n equals arr.length. Just so that when we're talking about this, we're talking about by growth of n, for our time complexity. So in bubble sort, we did a for loop and a for loop. This time we're going to do similar-ish, but we're going to do a for loop and a while loop. Still a nested loop, still O of n squared, worst case scenario, big O of n squared. So quadratic runtime at worst case. So let's have a look. We'll make a for loop, like for an outer loop. We're still going to kind of keep with the same sort of naming convention. So I'll have int I. Now what I want to do is I don't want to start from 0 here. I want to start from 1 because the inner loop is going to start from 0. Or rather, it's going to start from I minus 1. So while I is less than n, I'm going to do I plus plus. Now, first thing we need to do while we're in here, I want some sort of a key, which is going to be something to move around the place eventually. It's going to be inserted somewhere. But the while loop is going to kind of decide whereabouts things are going to insert. So let's make it int key, and that is going to equal whatever's at ARR at index of I. Then we're going to make a new secondary index. So int j is equal to I minus 1, so it's to the left. So that's the first iteration, it's going to be 0. Now we can do a little while loop. So while j is greater than or equal to 0, and secondary stipulation is that we want the, basically while the key is actually, let's see, so while the current array at j index is greater than our current key, Then we want to kind of move that data across. So we can do that. So what we want to say is, well, ARR at J is greater than key. So while this is true, what we want to do is we want to take ARR at J and set it, and insert it inside ARR at J plus 1. So we're moving it over to the right. Yeah, hence insertion. But this isn't actually inserting. It's kind of making space and keeps making space until it finds the correct spot to insert the key. At this point, we need to decrement J. It's kind of going, move over, come over here, move over, come over here, move over, until you eventually find the correct space for the key. So at this point, we can, so we need to decrement J. So J minus. Save that. After that's happened, we now need to insert our key in the correct spot. Now, the correct spot would be J plus 1's index. So ARR at J plus 1 equals key. Okay. So the other thing that I want to do now is some driver code to actually run it. Now, luckily, we already did this in BubbleSort. So instead of actually rewriting everything from scratch, I'm going to literally copy paste for the win. Here we go. We're going to have to change a couple of, well, we're going to have to change kind of one thing in this. Let's copy that. Okay. Paste it in here. Basically, we don't want to do a bubble sort. We want to do an insertion sort. Save that. Now, let's see if there's any typos. We can try and compile this and see if there's any typos. It's going to just set up an array. It's going to print the unsorted data. Then it's going to sort the data and print the sorted data. So let's do that then. Let's go, okay, I want to do a Java C on insertion sort.java and see what happens. Well, we don't seem to have any errors and it's created the class. So now let's do a Java on insertion sort. As you can see, we've got our 2, 3, 1, 4, 7, 6, 5, 8, 9, 0. That is now sorted to 0, 1, 2, 3, 4, 5, and so on. So we can further now think about what really is we kind of inferred that it's going to be the same worst case scenario as bubble sort. And we can find that out and look at it by literally just assessing that. So we've got this, we'll call this O of 1 for now. This one's constant. For loop's going over sort of in relation to n. Therefore, we can say this one's O of n. This is another O of 1 and O of 1. And when I say O of 1, I just mean constant time. So O of 1 could be O of 2, O of 3, but it's constant time. Same again, the while loop is in conjunction to really J. But J is based upon n. So it's almost, like I say, in worst case, it could be in relation to, it's going to be in relation to n in some way, shape, or form. So in worst case, when we're talking about big O, which is worst case, it's going to be O of n. Then again, we'll say another O of 1, but again, this is technically doing a single set. That's O of 1, and it's also no, I think that's pretty much it. That's O of 1. Same again, O of 1 here, and we've got another kind of O of 1. So if we add all these up, we've got 1, 2, 3, 4, 5, 6, O of 6, which is still O of 1 as far as we're concerned. Now we've got this O of n and O of n, but if you'll notice, this is nested. So if they're nested, you have to multiply them together. So it's n squared. So when we think about this, we've got technically O of n squared plus O of, what was it? 1, 2, 3, 4, 5, 6. Now, here's where we go, okay, well, let's get rid of all these constants. So that becomes O of 1. Now, only take the highest cost. So the highest cost is this one. So we can ignore that O of 1. So it becomes O of n squared, or quadratic. So it's big O notation. Time complexity is quadratic time complexity. Worst case. Okay, that's pretty much it for insertion sort. We now have our sort of concepts down. We have an algorithm. We have tested it using some base data to start with. We've been able to do our sort. Both seem fairly fast with that size of data. The larger the data gets, the worse we're going to get. We're going to get O of n squared. So if it's 10 items, it's going to take 100 iterations because it's 10 times 10 at worst. If it's 100, it's going to take 10,000 iterations. So there's a big jump there. So it's literally number times number. So that's quite a big iteration. You know, in smaller amounts, that's not too bad. We're talking a few milliseconds here, a few milliseconds there, but it still could be improved upon by using a different form of sort. Okay. So it's been awesome making this video, and I hope to see you in another one. We might make maybe a merge sort next. Have a good one. Bye-bye.